Hello, hello. Hi. Hello, everyone. Well, it's a pleasure to be speaking today about something very interesting that we are going to be spending the next 50 minutes more or less talking about, which is this thing that's called homoglyph attacks, right? But before we get started and we understand what this is about, etc., I'd just love to give you some notes about what we are going to be talking about, how the presentation is going to work, etc. So the first thing is that, well, whenever you make any presentation, right, you have to choose if you're accessible or super precise about things. And I think it's more important to be, well, just understood and accessible. So that's what I'm gonna go for. But if you want the precision, the details, I'm gonna put something here. I'm gonna put the references so you can take notes. And at the end of the presentation, I'll give you a QR code with all of the bibliography. So if you want like the specific data, etc., it's going to be there. Now, we are going to have some sections in the presentation, and at the end of each section, we are going to have a pink box, like this one. What we are going to do is simply remember those pink boxes, and at the end of the presentation, we are going to recap. We are going to summarize using the pink boxes to remember the whole thing. So whenever we see a pink box, that means remember this. Then, of course, I imagine you've seen we have some bingo cards on your chairs. I'll explain that in a second. But having said that, I think we are more or less ready to get started. So let's dive into homoglyph-based attacks. Just a few words on, well, who am I, etc. before we talk about that. Something I really like to do is research. I love to do a lot of things. You can see this is like a workload of things I did. I took my CV and I put like all of the words here. One of the most important things for me is this one. And specifically, I'm going to be talking about, well, one paper that I just published about this thing. It's in Calling. I don't know if you know Calling, maybe. It's the Conference on Computational Linguistics. Well, anyway, homoglyphs. That's the topic of the presentation. Let's understand what this is. And we're gonna start, of course, by just getting like a general idea. Okay, so let's say you have some letters like this. Okay, and now I'm gonna ask you, if you press the letter A on your keyboard, what do you think comes up? Which one of those says, they are all sort of A's, right? But if you press A on your keyboard, what would you say? Is it the first one, second one, third, third one, fourth, fifth, fourth? Okay, well, it's actually the second one. It's the second one. You see the difference is that they have different Unicode encodings, right? So the numbers, the things that the computer sees are different, and that's the key here, homoglyphs. And this is the important part, is that are characters that look identical, but they don't mean the same thing to the computer. That's the key here. They have different encodings, and that's what we are gonna use. Now, we are ready to understand what this bingo challenge is about, right? In your bingo cards, you're gonna have some homoglyphs like these ones here. I'll just make a note. There's some homoglyphs that are visible. These ones are visible, right? Like we have, like, for example, like some letter E's with like accents, etc. Those are visible, but some homoglyphs are literally indistinguishable. Some homoglyphs, like if you had them, of course I didn't put it in the bingo cards because then you wouldn't be able to do the bingo later, but some homoglyphs are literally the same letter. Like you wouldn't be able to just visually tell them apart. Now, what we're gonna have is that in some of the slides of this presentation, some of them, we're gonna have some homoglyphs, okay? You're gonna have to pay attention and try to spot them. And if you get to spot a line of homoglyphs, then I'd love you to raise your hand, stop me, and tell me, hey, I have a line, okay? Bingo card. Very good. Now, one small detail about this is that you won't find all of them. That's on purpose. Some of the homoglyphs that are on the card are not in the presentation. That's just to make it like a little bit more tricky, okay? So just pay attention to the slides. We are gonna have the homoglyphs, but not all of them, okay? Understood? Very good. Oh, and just another detail is that I'd love to give you pens, but I didn't have so many pens. So you're gonna have to take notes or, remember which ones you've seen along the presentation. Now, let's continue. And I'd just love to give you a very brief overview of what's the history of homoglyphs. This is not like a new idea. It existed before. And specifically, I'd say that there's two main things where homoglyphs were used in the past. URL attacks, you know them, right? I get this SMS on my phone, I click, it's not the real website. Now, what happens today? We have a solution for that, which is called Unicode. Basically, when I click on a link that has like homoglyphs, it gets converted into that weird string that doesn't look like PayPal at all, right? So that's patched, but it was a vulnerability in the past. Another thing that we can still do, because this is just, discipline in itself, is hiding information or steganography. Essentially, basic idea, just imagine I have a text like this one. If the first A is an alpha, then you do something else, right? I'm just hiding information in plain sight. So homoglyphs in general, this is a pink box thing to remember, characters we can't discern. They look the same, but they are not the same. So that's it for the first section. Now let's talk a little bit about how AI-generated text detectors work, because that will be very important for the rest of the presentation, right? So I'd say that there's three main types of systems that you can use to be able to tell if something has been written by ChatGPT, Gemini, Claude, etc., or not. So human or AI, right? The first of them is what we call a classifier. So, well, I don't know if you know about AI, machine learning, language models, etc. What would you say? Like, how familiar are you with those things? A lot, a little, more or less? Okay, mixture of expertise. Very good, very good. Well, to understand classifiers, we just need to understand that we get a text, and we get this text, and we give it to a model that generates something that we call an embedding. What's an embedding? Well, for the purposes of this presentation, it's just a point in space that we can represent. So for example, we give a text to a model, right? And we get a point in space. That could be that arrow here, like that red dot in space. And that means that, well, it's in a region of points that's AI generated. So very simple idea, right? That's what classifiers do. They just, allow us to put something in an embedding space and say, okay, this is my text, right? Like this is generated or this is human. Very good. So now let's talk a little bit about perplexity-based detectors, right? This is another type of detector, and this is very interesting. But to understand how they work, we need to dive a little bit deeper into LLMs, etc., etc. So I'll just give you the very basic idea. LLMs are basically playing a game of fill the gap all the time. So if I give you this sentence, as a hobby, I like to collect fill the gap, what's going to happen here? Well, I take my LLM, my language model, and I just give this sentence to the language model, right? And what it's gonna do is just giving me this probability distribution. So what can we see here? What we can see is that, for example, the model is telling me, okay, I think that things is 30% likely to come after those words. books, for example, 22%, etc., right? So it's just giving me a probability of the different words that could come after this. And what we do is we just choose one of the words on the top of the distribution and we complete the sentence, and then we repeat the process all the time. So how do we detect if something has been written by AI? Well, very simple idea. If we have a text that's human written, it's likely that the words in that text will not always be on top of the distribution. You know, humans are more creative, so it's likely that at some point the human will choose something that's, for example, 0.01% likely. So that's the whole idea of how we do the detection of generated text using perplexity, which is another measure of probability, right? If I have something that's AI generated, I'm going to have low perplexity. I'm not going to be surprised when I see this text if I'm a language model. But if I have something that's human written, the likelihoods of the things are going to be lower. So that's how we do the detection. We just repeat this process for the whole text, and then we get a prediction. Very simple. Now, third type of detector. Okay, we've seen two already. The third one is very interesting. It's watermarking. And you've probably seen something about this because it's in the media sometimes, you know, like there's news like OpenAI has like their watermark, they may release it or not, etc. This is, to me, the most interesting system. And I'm gonna give you a simple idea of how this could look like. So we have our probability distribution again, but now when we choose our next word, we're gonna do something special. Okay? What are we gonna do? We're gonna use a rule. And the rule is gonna be, you pick the nth word in your distribution. How do you choose that word? It's the number of characters in the word before that one. So, for example, as a hobby, I like to collect, right? 7 words. So we go to our probability distribution. It's here again. We start counting things, books, stamps, coins, postcards, shells, and plants. So that's our 7th word. We pick that one, and that's our completion. And it can only be that one. It needs to be number 7. Okay? So if we do this thing, we start having a sort of chain of completions, right? And if we change just a single word, then it will stop matching our rule, which means that when we try to detect the text, we will see that if it was written by ChatGPT, for example, and it follows the watermark, we would expect that all of the words would always be number 7, 5, whatever. It would always follow this rule. So that's a very simple, but also statistically very efficient and really reliable way to detect if a text has been generated. Watermarks are really good. Now, the idea is that we repeat that for all of the words. Again, if a lot of words follow this rule, it's AI generated. Now, I'm just gonna make a side note here. This thing of the watermarks is really, really interesting. Just, I'm getting aside for a little bit, because if you think about it, like the thing about watermarks is that they're very reliable, very reliable. They give you a very statistic confidence that a text has been written by an LLM. And the thing is that right now we don't really know what's the watermark in ChatGPT or, you know, those LLMs, but that doesn't mean that it doesn't exist. So when you write something with ChatGPT today, you're gonna have that watermark. And in 5 years from now, maybe OpenAI will start selling a new service. Detect if this text has been written with ChatGPT. So whatever you write today could potentially come back to haunt you in 5 years from now if OpenAI decides to release their watermark or something like that. Side note here, I'm just gonna leave that aside because it's not the topic of the presentation, but just keep that in mind. Maybe someday it could be helpful to remember that. So, general idea, pink box. The detection of generated texts can be done with different techniques, right? So now you can probably imagine, well, we have some homoglyphs here. What happens if we start using this thing to attack those detectors? What happens if we replace some of the characters? Well, let's do a demo. Let's see what happens, right? So I'm just gonna go here, and this is just a a website that like just lets you replace some characters. I have an input text here. I'm just gonna copy paste this, just paste it in some detector, right? It's gonna check this text. Oh, okay, very likely AI, right? Very good. We were expecting that. Now we can replace. Oh my God. Oh, sorry. Sorry. Okay. So now you should be able to see it, right? Yes, 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 yes. Okay, here we are. So some text, right? Copy, paste. We go here. I pasted the text, and I run some detector. I checked if it's AI or not, and it says very likely to be AI. Good. Expectable. Now, let's see what happens if instead of that text, I take a text that has been replaced by some homoglyphs, specifically 5% of the characters. Okay, so that's the one on the right. I'm just gonna copy this text. Copy, go here, and paste it here. Okay, very good. So let's see what happens. Oh, well, this one is very good. But let me show you here. I'll show you here. Some detectors could implement what we're gonna talk about at the end of the presentation. That's the best detector that you will find, honestly. This is a regular detector that doesn't do pre-processing for the text. This one does pre-processing, so it removes homoglyphs, etc., etc. We're gonna look into that at the end of the presentation. But this is what you usually see. Your text suddenly seems to be human. And that is very, very important here. Because now, and I'm gonna go back to the presentation, now we have seen that most detectors are vulnerable to this, right? Not all of them, but if you don't do pre-processing in your text, well, your text just becomes unrecognizable. It's obvious it would not really work anymore, right? So what's the technical analysis of this thing? What happens inside of the detector? What's going on inside of, for example, the classifiers? You remember we had something like this, right? We had some AI text in red here, and we had some blue text, which was human. Now, if we attack the text with homoglyphs, we get something like here on the right. What can we see here? Two things, two important things. First thing is, that text is in a different region of space. So that means it's very hard for you to say this is red or blue, right? Because it's in a completely separate area. So if you just have this classifier, it's gonna sort of go crazy. But even if you were able to sort of retrain your classifier, etc., etc., you're gonna have something else that's different, which is the points. They are super mixed. You have purple points, green points, all mixed together. So it's really hard to draw a boundary here. Even if you addressed the problem by retraining, etc., etc., a lot of mixture. So that becomes really hard, really hard. Now, what happens here with perplexity-based detectors? You remember they were those detectors that took a sentence like this, right? And then analyze the text to see what was the probability of the word, etc., etc. Well, if our text looks like this now, we have like some characters that are not really recognizable, some things that we can't really tell apart. Well, of course, that word is going to be super, super unlikely. It's going to be at the bottom of the distribution. So, well, it's going to be classified as human written. Now, watermarks. What's gonna happen with watermarks here? Very interesting again. So that's the example that we had before, right? Seventh word, matches a rule, etc. But now let's put some homoglyphs here. Here we are. And our rule is, again, pick the nth word, blah, 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 blah. We go here. Well, we don't know what that weird character is, right? So maybe it could be a space, unknown character, etc. Let's pick the fifth word. Postcards. Oh, well, it's not plants, right? It's not what we have here, so it's not following the rule. It seems to be human written because, again, it doesn't follow this rule. So classifiers, evaded. Perplexity-based detectors, evaded. Watermarks, evaded as well. Oh, well, that's a problem because all of these mechanisms of action can exploit sort of this confusion idea, right? The detector can't really see the text anymore, so it stops working. But does it really stop working? Well, let's see some experimental results. So I'll tell you what I did. I started with 1,000 human texts and 1,000 AI texts, okay? Data sets of generated texts. And then I just replaced the text with different percentages. So 5% homoglyphs, 10% homoglyphs, 15, 20, everything you can replace. Those are the attack data sets. Now, we have a bunch of detectors. You know, there's different ones in the market, etc., etc. And we get some baseline results. The baseline results are basically what you would get if you didn't apply any homoglyph attack, but you also get the results of what happens when you attack the text. And the results, I'm just going to show them to you now, are very interesting. So this is what we get when we don't have an attack. This is just for one detector, one dataset, right? And well, what you can see here is that the detector is very good. We can see that we have this diagonal here, so it means that the texts that are human are generally being classified as human. The texts that are AI are classified as AI. Now the question is, what happens when we attack the texts? That's what we're going to see now. All of them are, well, classified as human, but not all of them are human. Is this the case in all of the detectors? Well, I'll show you the general results. So again, we have like a set of detectors, right, in different data sets. And we can see that some detectors are very good, right? For example, this one. Some of them are not so good. There are, well, some detectors that didn't have a very good baseline, but some of them are really good. So what happens to them? Those are the general results. It's very bad. So we need to do something about it, right? Well, yes, we'll talk about this in a second. The idea in general, pink box, is that this is in general very effective. Homoglyphs still work nowadays with most detectors, and this has a series of implications. So implications like Twitter bots, cheating, fraud, you know, all of the things that you could think about, those interesting things. But if there's a key idea here for me is that this is a very simple technique. Everyone can do it, right? It's not hard to replace homoglyphs. The other things that you can try to do to evade detectors are, okay, let's use an LLM to paraphrase the text. So, you know, let's use ChatGPT to rewrite the text, to change some words, etc. But there's a problem here. You need computation resources, you need access to an LLM, probably one that's not watermarked to not get tagged as this text has been rewritten by this LLM, etc. So that's a problem with the main techniques that we have to evade detectors, but this one is different. You can do it with a very simple script. We have like you know, a lot of tools that can do homoglyph substitution. So that's complicated, right? Can we do something to prevent this? What are the safeguards we can implement? Well, this is where it gets a little bit into work in progress, because that's you know, something I'm working on right now, literally right now. It's what I'm working on. But I can tell you, one of the things that we can do is input constraints. Okay, so what I mean by that is that we can have our AI generated text detector like this one, and we just put another box, which is a detector of homoglyph attacks. So just an alarm. The idea is we have a text, we give this to our homoglyph attack detector, you know, it analyzes the text, and if there's no attack here, we just run the text through our original detector. But if we now have an AI generated text, we repeat the same thing, and we will see that this text has been generated by an AI. The different case here is that if we have an attack text, that we can't really give this text to the detector because we know it's gonna fail, right? We know it's not accurate, so we need to detect this beforehand. That's the role of the homoglyph attack detector. And, well, we could just try to do it just checking if there's homoglyphs. You know, we can define a list. These are the list of different homoglyphs that you can find in a text. If any of those are present in the text, you just raise an alarm. And you never give this text to the detector, you just skip this completely. And that's what you do. Is that enough? Well, maybe not enough, right? Maybe we need to get a little bit smarter than that, because sometimes you have texts like this. This is just like a random text I took from a scientific article. You can see that we have homoglyphs here. So yeah, that's a false positive. And well, maybe we should change our strategy a little bit, but we can do something pretty simple. We can just take a rule-based approach. What I mean by this is that, for example, we can just calculate the percentage of words that have mixed characters. So, for example, we have, you know, a few words here. What's the percentage of them? If we just base ourselves on, well, maybe 5% of these words have mixed characters, etc., etc., we can solve the problem. Can we do it like that? Just give me a second. Oh, is it because of the bingo? Okay. So just let me show you the results here, and then I'll take your question. So what we can see here is that when we apply this solution, it works very well. It's really, really effective. We can see that if we just have like this naive approach of raise the alarm as soon as you see any homoglyph, it doesn't work. It's not enough. But if we use a percentage, something like a rule-based approach, that's when we get a really good performance. That's very good. Yeah. No, 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 of course, go ahead. So, well, so what you can see here is that we have the area under the curve of the receiver operating characteristic. That's just another way of saying that I'm not choosing a threshold here. Basically, this means if you were to choose the best threshold here, you know, the best percentage, would you be able to detect all of the texts? And what this is saying here is, well, if you use a rules-based approach and you choose wisely what's your percentage, you get 100% of them. So you would be able to tune your rule so that you catch all of the texts. However, that's the case in English, right? But we have other languages in the world. And what happens if we consider other languages? Well, maybe the results are not that good. This is, for example, for the second most spoken language, Mandarin. Rules don't really work here. So, is there something we can do? What, how can we solve this problem? Any ideas? Sorry?
So you see, you show that they are grouped together, so you could look at how they are paragraphs are
So you mean,
put together.
so you mean like, for example, if I have like a Latin character next to a Russian character, something like that, or
You like write, what's the purpose of what you're writing? Right? Are you writing a scientific paper? So when you do scientific papers, you could then go in
mm.
and you can say, okay, this is a formula. You could identify this as a formula that contains characters.
So the idea here is that you would analyze the text, detect, okay, this is a scientific text, so my threshold here is different because, you know, I expect that I would have some characters in Greek, for example, Greek letters, things like that. I just change my detection rules, sort of, right? That's more or less the idea. Well, that's something we can try, right? And so to be honest, I don't have evaluation results on that. What I imagine is that for some languages it would work, but maybe we can do something else that possibly works better. Okay? Yes. Let's see, let's see. So I'm gonna give you two ideas. Again, this is work in progress. So this is what I'm working on right now. So this is subject to change, etc., etc. And I'll take your question in a few moments because this is a really important part of the presentation. So if that's all right, I'll take your question in a moment, okay? And I'm just gonna give you two ideas that we can try to address it. Oh, bingo! Oh my God, yes, very good. Okay, who was the first one? Very good. So I'll go talk to you at the end of the presentation, okay? Very good, nice. Good job, good job. Very good. So, two ideas here. Well, if so, the goal that we have is that we really want to be able to address the issue in general for different languages, different contexts, scientific texts, I don't know, texts in Greek and in Mandarin, etc., etc. One of the ideas that you could think about is analyzing tokenization. So, what's the idea here? Well, you can have a text like the one on the left, right? Normal text, not attacked. But when you attack the text, you have some characters that change. They look the same, but you know, I just highlighted that in red here. So what happens here? Well, when we tokenize the text, and that means when the system starts to process the different words, it's gonna give me different representations. And specifically, what happens is that I get a lot more tokens. For the same text, I get a lot more elements in the list. Why? Because the tokenizers are trained to minimize the number of tokens they generate. So for example, hello is a very simple word. So it's present in a lot of phrases, right? So when a tokenizer sees hello, it doesn't generate the tokens for H, E, L, L. No, it doesn't do that. It just generates a single token, which is hello. Just one single element, right? But now if I start having homoglyphs, what's gonna happen is that the words are gonna be split in smaller things. If I add a homoglyph in, for example, the E of hello, now I'm gonna get a token for H, probably a token for that weird character in the middle, and then maybe L and LLO. You know, I'm gonna get more tokens. So that's the key idea here. Of course, we don't know what's the original text, right? That's something that we don't have. But what we can do is that we can define a normalization function and just go back to what we had before. So attack text, we go back, and we get a sort of our version of what we think would be the original thing. Now, we simply check what's the difference between what I think would be the unattacked text and the attacked text. And I see that in the attack text, I have a lot more tokens, blah, blah, blah. So I define a ratio, right? For example, if it's more than 1.5, then that means I have an attack here. The idea, the key point behind this technique is that if you're dealing, for example, with a scientific text, you would get those tokens that include, Greek letters, etc. But still, the tokenizer has learned to represent that. So it's not going to be just perplexed when it sees something like sigma algebra or things like that. It's still gonna tokenize that thing correctly, so you're not gonna have this huge gap in the number of tokens. And that's the key insight here. So that's the first idea. Now I'm gonna give you a second idea, which is perplexity. Perplexity. You remember we were talking about this a second ago, right? We had some slides where we were seeing, that we had like some distributions and we were checking where the words are, etc. So this is what we are gonna do now. Perplexity. Let's take a look at that same sentence here. Okay? So we have this one in blue here, and we have this one that is replaced in red. What can we see? What would you say? It's going lower, right? Yes, that's the thing. It's going lower, and we can see that in general, like the thing that's not attacked, it tends to be in that region, and then we have the other thing that's attacked below. Let me just say that perplexity values, or well, what we have here is log likelihood, which is another vision of the perplexity idea. They are not very useful as a comparison between different texts. So what I mean by that is that, for example, if I have the US Constitution, it's going to have low perplexity because it's a text that everybody knows. So that's a type of text that has very low perplexity. But if I have something that's very creative, a poem or things like that, that's usually going to have a higher perplexity. So just comparing the values of perplexity itself is not enough, but what we can do is we can compare the difference, again, the ratio of perplexity, right? We can see that that's different. The distribution of perplexity changes. And that's what we should try to use. Specifically, we just need to normalize the text, just go back to what we think would be the original version, and then we define another ratio. So the idea here is to have those sort of ratios, right? For example, in the case of the US Constitution, if I don't have a homoglyph attack, I get the same text. So my ratio is just going to be 1, no change whatsoever. If I had an attack, my perplexity is going to lower because now the system starts to understand what's written here. Let's see how this works in practice. I've tried to implement this, so I'm just gonna exit the presentation so you can see the screen. And let me go here. So this is a simple website I set up for just demoing this thing with you. And I have some interesting examples to look at. So the first thing is, what happens if I just use a normal text? Well, of course, the ratio is 1 because I don't have homoglyphs, so it's going to be all the same, right? Very basic. Now, what happens if I have a 5% homoglyph attack? That's what happens. I get this, well, the ratios are different, of course, so we trigger the alarm. Very good. This is what we would expect. Well, we can try this with another text, etc. But maybe what's more interesting is to see what happens with a text that would naturally contain homoglyphs, right? This is what we wanted to check, the scientific article example. And that's the key insight. The difference in tokenization and the difference in perplexity is not enough to raise the alarm. That's super interesting. Now, let's take a look at another example. For example, this is a text about languages, right? What happens here? Same thing. Not enough to trigger the alarm. But perhaps what's even more interesting is what happens if I have a text that already contains homoglyphs. So for example, a text that talks about languages, and then I have an extra attack on the text. So for example, I have a text about Spanish here, right? On top of the homoglyphs that we naturally have in this text, I also attack the text with more homoglyphs. So we start having a lot and a lot of homoglyphs in this text. Well, this is very interesting because the alarm still gets triggered. The difference, the ratio, is enough to trigger the alarm. And that's the key. Very interesting. Now, my question for you would be, what do you think works better? Tokenization or perplexity? Who's for tokenization here? Tokenization. Okay, I can see some people for tokenization. Now, perplexity? Well, we're divided, right? Some people say perplexity, some people say tokenization. Both of them. Yeah, hybrid approach. Well, I'll give you the results because maybe there's no need for going for one of the two. Which one of them is it? It's perplexity. Why? Well, this is something, again, work in progress. So I'm looking into this right now, right? But for example, for Mandarin, we can see that the results, when we just analyze the tokenization, are better. If we are to define our threshold in the best way possible, we are able to better classify those texts. Question, does this extend to other languages in general? Is this something, a result that we could potentially generalize? Well, what do you think? Do you think it applies? Yes? Yeah? Well, yeah, indeed, that expands to other languages. Of course, the naive approach is very bad. So here, what I did was I took the C4 dataset. I don't know if you know C4. It's basically, so you know ChatGPT used like a lot of websites to train its system. This is that dataset, essentially. So here we have, websites from all around the internet, like in 97 different languages, talking about a lot of different things, scientific things, just I don't know, texts about cooking or whatever. We have 97 languages talking about completely different contexts, and still we can see that tokenization does very well. It stands against, a lot of different languages, contexts, etc. That's very nice. But on top of that, I'm going to give you another advantage of tokenization. If that was not enough, let's talk about computation cost, because that is very interesting as well. So what we can see here is that essentially, oh, sorry, this is not perplexity, this is naive. So the naive alarm is very low in computation cost. Of course, it's very fast, right? Like we just need to do one check. Is there a homoglyph in the text? Very fast. But if we actually go and we check for all of the words, does this contain like a mixture of alphabets, etc., etc., that changes the thing. That's the rules-based approach, and it's, well, a little bit worse in performance than the tokenization approach. Why is that? Because tokenizers are very optimized. So they are written in Rust usually, and that means that we can really be very fast when we tokenize any text in general. So that's super fast, and we can see that perplexity, well, it's much worse. And this is a log scale, so it really goes up a lot. So tokenization in general, my idea, and of course, again, work in progress, could change, but my idea for now is that tokenization works really, really, really well. Really well, it's fast, it's reliable, it's what I would definitely, definitely go for. So I have no reservations here. It's really good. Maybe my only thing that I would add here is that you can see that, well, there's still a little gap, right? This is what's in future work. Of course, when you do research, you can't solve everything at the same time. So that's what I'm gonna keep looking at. How do I solve this 5% that's remaining? Maybe one idea would be to consider differences in context, you know, and just try to adapt thresholds in different languages, different like styles of writing, etc. But in general, I'd say that there's some work to do here. That's on us. We need to keep innovating. And let's just try to wrap up a little bit now. First of all, the bingo. Okay, where were the different letters? Well, some of them are hard to catch. So one of the things that we had, I don't know if, who caught this one? A few hands, yes, very good. Then we had the papal one. That was maybe a little bit tricky, right? Because it looked like just one example, so I thought, well, some people might not get this one. But did you see this one? I think this one was easy to see. Maybe the hardest one for me would be this one. Very good, nice. Yeah, this was very hard. Do you see it? Yeah? It's here. So it's that letter D with a small dot here. Yeah, it's very hard. I removed the punctuation to make it even harder, yeah. Uh-huh, yes, yes. Very nice catch, yeah, that's true. I removed the final period here to make it like a little bit more tricky. Then, what else did we have? This one? Yes, very good, very nice. Did you see that? No? Can you see it now? That P, right? It's sometimes it's hard to catch. But this one? Nope. Yeah, sometimes it's a little bit complicated. But that's the idea of homoglyphs, right? That's why they are so effective. So, yes, it's a very good vector for attacks on homoglyph, on detectors in general. But I'd say I hope we've learned something. Specifically, we saw that homoglyphs are characters that we can't really discern. You know, we don't really know straight away if something is a homoglyph or not. Those were easy ones, but sometimes it's even harder. Sometimes there's no difference at all. We also saw that the detection of AI-generated texts is done with different techniques. So, you know, classifiers, perplexity-based approaches, watermarks, etc. And what happens when we do that is that the text becomes really unrecognizable. It's very hard to understand what's going on here, so we confuse the systems. And when we exploit this, our attacks become, well, super effective. Those detectors don't work anymore. So that's what we saw. And on top of that, there was another risk here, right? It's super easy to do this thing. So the access barrier for this, super low, super low. Everyone can do it. However, there's some ideas we can try. We can try to pre-process the text. We can try to do what they were doing, for example, in this detector I showed you, when they just, you know, pre-process the text, remove homoglyphs, check if something's different or not. And that's something we can try. And when we do that, we get more or less good results. Still, there's this small gap we have to keep working on, but we have some ideas we can try. There's some work we can do. So we need to keep innovating. This is where I give you the QR code with the bibliography, with the references. If you want to check anything else, that's here. But also here you have a feedback form. So you can tell me what you would change, if you would do something differently, etc., etc. And now I'll take questions. I'll start with the question that you wanted to ask, or maybe now it's clear, right? Yeah. Any more questions about what we saw here? Yeah.
Particle with lots of hieroglyphs, and I replace them with their default characters. How easy would detect that using the same approach, or would you need to do something different?
So you mean that, you know, I have a text that naturally has a lot of homoglyphs, and then I start replacing that by the normal versions. What happens in this case? I'm just repeating that because we have like the live stream here. Well, if we do that, that's a little bit what I tried to show in the demo that we had before. You know, we had this text that was a Spanish text talking about the language, etc. It was saying some things about, I think, verbs in Spanish or something like that. It had like accents, etc. When we do the attack, what should happen here is that we are seeing a text that's talking about Spanish, but then we don't see the accents where we expect to find them. So the tokenizer would probably not tokenize those words well. For example, if we have a verb that in Spanish always has the accent and then it doesn't have the accent, it's going to be broken down into smaller words. And if we analyze perplexity, it's going to be more or less the same idea as well. It's going to go into the LLM. The LLM is going to try to analyze that. It's going to be low in the ranking that it makes. So probably, again, this needs more checking, but probably what's going to happen is that you would still be resistant to that using ratios. Of course, if you use more naive approaches, then that's where it breaks down. But yes, that's I think those are very good tools that we can utilize. And let me go to your question now.
Consider an attack that knows about your technique using tokenization. Can they do something to make it even harder to detect the
So can
like
like
to insert the homoglyphs in the right box and like tailor because they know that you are doing tokenizations on
mhm. So your question essentially is, can we try to optimize those attacks so that we have, let's say, an extra performance attack which is able to target the fact that we know that we have tokenizers, etc., etc. And even if we apply those ratios, we evade the detectors? That's a great question, and I don't. So to be honest, I don't really have a very specific answer, right? Because, well, I haven't really looked into that, but I'm just gonna give you my impression, what I think would be the answer. And I believe that there's some degree to that. So probably you would be able to try to optimize that, maybe putting, yeah, your homoglyphs in places where your tokenizer would not break down the words into smaller words. For example, maybe if you have a letter in, you know, in a very specific place, or single words that are just one letter, like for example, A or well, I can just think of A, you know, but if you replace that A, maybe that works better. You know, you wouldn't have this change in tokenization. So probably you can try to optimize that. Is it enough to trick all of the detectors? I'm not sure. But I think that there's some degree of optimization that you could do here, yes. Any other questions? Yes. Mhm. That's a great question. So essentially, the question was, what happens with other types of attacks, like inserting spelling mistakes or rewriting the words, changing some, you know, positions of the characters, maybe inserting extra spaces. That's another thing that you can try to do. Well, the answer to that is that it's more or less analogous to what we saw here. So homoglyphs are essentially, the idea of homoglyphs is that the text becomes unrecognizable. If you insert spelling mistakes or if you introduce like some type of artifacts into the system so that it's not detectable anymore, you're going to have more or less the same effects. Complete evasion, detectors stop working, etc. You could address that with those techniques, I expect, but that's more work to be done as well. Yes. Any other questions? So, well, we are gonna wrap it up here, but I'm gonna be here for the whole conference. So if you want to talk about anything, just talk about homoglyphs in general or the detection of generated texts. That's something I've been working on for a while. I'm here for any questions. I'd really be happy to connect with you. And if you want my, LinkedIn, those things, it's also in the QR code. So thanks a lot, and I hope to see you here. And I'll talk to you about the bingo as well. Thank you.